Let me introduce Dr. Arunkumar Palaniappan. He is the resource person of morning session. He is the alumni of E&I. He completed his BE in Electronics and Instrumentation in the year 2003. He completed his MS in Coventry University, UK. Then he completed MBA and then proceeded the Doctor of Philosophy, that is PhD in Embedded System in 2022. He started from Mindtech from 2004 to 2007. Then he moved to Caterpillar, then Cognizant, Vestas. Presently he is in Enlighted. He is the Senior Manager, Hardware Engineering. Then he has honors like Special Prize for leading the Electronic Voting Machine team. Then presented a prize-winning white paper and a technical presentation in TechFest. Then he got the Best Initiative Award. He has a wide publication and a patent in analysis, design and real-time implementation of tamper-proof electronic voting machine for test. Let me invite Dr. Arunkumar Palaniappan to present the session.
I studied under Vinoda ma'am and Shaktivel sir, and I am alumni of E&I department. So this is like a dream come true to get introduced in the same department, right? So this is a dream that I long cherished. So we'll discuss about real-time IoT applications of IoT in agriculture and its simulation strategy. Okay. The real-time applications that I'm going to show is probably very common across what you've seen in YouTube and all of those. But what I'm going to dive into detail is how do you simulate all of those? What are all the simulation strategies? How do you kind of pre-test it, subsystem testing and all of those? And what are all the tools used to simulate each component? So those will be my focus. And if time permits, we'll also touch upon one paper that I did along with my PhD, which is simulation of lane control algorithm. So this is my profiling shot as which we recently saw. So the structure that I want to kind of take through is introduction to IoT, IoT in agriculture, real-time applications, simulation strategies, tools and framework used, and a sample testing, how it was done for a lane control algorithm. So, are we there? Can you proceed there? So, IoT in general, there is a lot of talk, and the term itself was coined only after 2015, right? But the technology has been existing from 2008. So, we have been using 2G SIM cards and 3G SIM cards, and the data has been communicated via satellite, and remote monitoring was functional right from 2008. But the term IoT was coined in 2015 and later, where it all came together as one. because of 4G penetration and 5G penetration and a lot of Wi-Fi penetrations. Right? So IoT is network of physical objects or things embedded. The predominant misconception when it comes to IoT is software and IoT is data. No, IoT is also data, IoT is also software, but there is a lot of hardware involved for you to get that data. So that is why IoT is embedded things, Internet of Things. That things means hardware. Lot of times the hardware part is missed because the software is lucrative, high paying, and in high demand. Right? So with electronics, softwares, sensors, and network connectivity. So all of this place, there is equal proportion of both hardware, firmware, and software. So most of my content here would be focusing on the hardware side of it and the firmware side of it, right? And this is called the IoT edge nodes. So it allows objects to be sensed, controlled remotely, and all those. So this is general stuff. If we can step back a moment, right? Initially it was manual control. Then what happened? We started controlling all our devices using electronics. Then we controlled using power electronics. Then we controlled using PC, desktop PC situated near the equipment. Then we moved on to networked PCs through LAN. And then we moved on to PCs via internet. And then we moved on to something called, and that's when IoT started. Then we moved on to internet connectivity, mobile, and all of this. So if we can understand this evolution, and if we can visualize this, then IoT is much easier for us when we picturize those components. So how IoT works? Addressability, identification, sensing, actuation, embedded information processing, localization, and user interface. So communication and cooperation, there are a lot of devices involved in that architecture. So all has to communicate and cooperate cohesively without delay so that the system gets functional. Addressability and identification, we need to command the right device, monitor the right device. If it is an open loop system, you monitor. If it is a closed loop system, you command. So without this, we would be kind of wrongly monitoring or wrongly controlling. Actuation is again, you kind of enable it, right? And then embedded information processing. Now, let's say that you have a mobile, right? And you have a headset. If it is a wireless headset without any button control here, so there is only one processor in that headset and there is no control, so that there is no intelligence. Whereas there are headsets where you have buttons here, and then if it is automatic control here, automatic volume control like a Bose headset, so that is intelligence. So the moment the processing information is present in the last node of that spectrum on the embedded device, that is embedded intelligence. If the intelligence is present in the processor, it is embedded intelligence. If the intelligence is present in the network and then it is only commanded, it is only a control. Then localization, user interfaces, these are all for convenience. How friendly it is and all of it. So now, this is the base reference model for IoT, a classic reference model. Physical devices, connectivity, edge computing, data accumulation, data abstraction, analytics, and collaboration. So this part is the sensors part. All your sensors, microcontrollers, wireless connectivity, RF, all of this fall into this space. When more than one device forms through the network, so that forms under here, the data accumulation, and then there is a control here, right? So in this stage, in the edge stage, we use sensors, actuators, and embedded devices. In this connectivity, it can be either wired or wireless connectivity. So wired connectivity, some of the protocols is CAN J1939 Ethernet from automotive perspective, whereas the traditional RS232, RS485 is still in use. There are devices that are still in IoT world with RS232, RS485, SPI and I2C. Okay, so those will still be there, but just that previously it was outside the device interfacing with the PC. Now these are embedded within the device because of compact electronics coming in. From wireless, mostly today it is used as Zigbee, Wi-Fi, Bluetooth and any RF. So this is where the scope gets elongated. Now there is thread over Zigbee, LoRa, Low-Pi and all of those, right? So this space is going endless. There will always be both public and proprietary implementations here, depending on the security that is needed for the system and depending on the convenience and the data rate that is needed. Because the moment you go into public protocol, you are bound by the protocol limitations and you cannot go beyond that, right? But what that offers you is interoperability, so that you can communicate with the third-party devices, right? So now here, data accumulation and abstraction. Predominant IoT companies, whatever is kind of advertised outside, advertised here. They make market here, they make the market visible here, using all the Python, AI, data, machine learning and all of those. This place, where it is data, abstraction and accumulation. So the sensors have to provide the data and the data have to be processed and then a dashboard is given. So this is usually Power Builder and a lot of those, right? And then collaboration is human interface, because IoT devices cannot be installed on its own. So you still need a human to install those, and then you need a human to support them and connect them through RFIs. So this place is more of collaboration between multiple teams and multiple companies and technologies. So this is a generic open loop system. Like any system, you kind of monitor and then gather the data and then you send it to a centralized place, and then either if you stop the analysis, it's open loop. If you feed back into the system, it is closed. This process of input, process and output will always be there. The terms will change, the logic will change. But can we get away from it? No. Either it will expand or it will shrink. Either it will go vertical more or horizontal more. But this is space. Now, this is an important topic, right? So, always there is this topic of security over protocols for IoT. And can anybody tell what is the security algorithm that you know for IoT? That you have heard? Because IoT has all layers, right? But predominantly the moment we talk about security, what is that one algorithm that we keep on listening? Blockchain. But is blockchain enough? Is blockchain enough?
No.
No. Because if it is only the cloud layer, if it is only the data layer, blockchain is enough. But the moment you want to come into an embedded side, blockchain is not enough. So you need blockchain along with the RF algorithms.
Along with the
RF security algorithms. So the BLE, now the reason why I am touching BLE is that is something that we use on a regular basis, so you can relate to it, right? When you pair a BLE device, today with the modern systems, you just hit a pair. But when we go one step backward with the 2015, 2016 devices, there will be a code that is displayed. And then you have to see the same code on both devices and press yes. So what is happening in the background?
verification and validation can be done.
So there is a security key that is getting exchanged, and there is a manual verification that you are doing.
Yes.
Right? So which means BLE has a proprietary security algorithm. Now when the same device is controlled through your internet, what happens is from that internet to that base device, it will be blockchain. And from the base device to the actual control unit, it will be BLE.
Sir, what you are saying is PLE.
BLE, Bluetooth Low Energy.
Bluetooth Low Energy.
Low energy, right? So same thing with any protocol. You take Zigbee, Wi-Fi, Thread, all of them have their own proprietary algorithms. Like Zigbee has 128-bit AES, and some other has a hashing algorithm, some other has a 1-bit shift algorithm. Some has 256-bit AES, 256 other algorithms, right? So the protocol standard define those. If you look at IoT security as a whole, just blockchain is not enough. The field that is still not explored is the security here. There is a lot of papers here, lot of work here, but here it is not, and this algorithm here, you typically implement in an embedded processor. On a C code, you implement and then you verify if the handshake is happening. You provide a wrong key, you provide a right key, and then you see whether the secure communication is happening.
But it is already have. Like the security algorithm is already there, right?
Yes, but there is no active work on the improvement of it.
Okay.
Active work is happening here.
Yes, sir.
Because this can be done with a PC.
Okay.
Here you need a lot of hardware.
Okay.
And here it is embedded. Here it is Python. So it's easier for somebody to get into this research space than here, because this is lucrative, easier, and you'll get the results faster.
Okay. Maybe the data storage, like for security algorithm, it will take too much of time, right?
No. That is why every algorithm, when
Talking
you,
in the perspective of that is embedded system, they are having limited storage. That's why they may improve they may not improve their qualification of this perspective of cybersecurity.
no, I would strongly deny that. The reason being, Zigbee was implemented in a 60K processor,
Okay.
60 kilobyte with 128-bit AES algorithm.
But in the
Okay, today we are talking about 320 kilobytes base memory and then extendable by RAM. So today memory is largely available. So memory, yes, I agree it was a constraint, but it is no longer. Today embedded systems come, or processor come with expandable memory. So you can have a peripheral memory and connect to the SPI lines or the I2 lines, and then you can still have it.
Okay.
So let's say you have a criteria where you select a processor,
Yes, sir.
Atmel processor, but your memory is not there. So then what the options they do is they put a SD card. And the SD card is talking to the processor through the SPI lines or to the I2. So your host image or the host code resides in the SD card. Processor is used for the boot up alone. You power up through the processor, and then all the execution happens there, and then control happens through the processor. So the peripherals are connected to the processor. So that type of architectures are also available. If at all we land up in a place where we see memory as a constraint. Okay. So this is using the same one, what is operational and what is information. So these are based on data and based on physical installations, and these are based on support. So these are pure IT side, like here you have to be on the field, and these are physical devices, whereas these can reside in the cloud and these are mostly invisible. Okay. So now this is how it comes. So the sensors provide us the data, and then there is an information that is gathered from the data, and then a knowledge is obtained from there.
Information.
Data, and from their information and from their knowledge and understanding, and then you are questioning. Evaluated understanding. So this is the data pyramid. Now all of the edge devices are here. The embedded intelligence is here. Sometimes when we talk about the sensors, auto-adjusting sensors. So this is a very common term, right? AI-powered sensors. What is AI-powered sensors? The sensors read the value, and then depending on how fast it reads and what all it reads, there is a correction that is happening, and then the actuator is kind of correcting it. Now, the sensor reads the data here, it processes, and then it corrects its algorithm, it reasons, and it corrects its algorithm, and then it controls. So all of this, when it resides in that one sensor, that is IoT edge, intelligent IoT edge node or AI-powered IoT edge node. The term AI is not fully defined. So the moment you put in marginal intelligence, companies use it for marketing, AI-powered. When we say Bluetooth compliant, it has to be 100% compliant. When we say AI powered, what is the margin of accuracy that you are looking? It is still not defined because the market is evolving and the companies are capitalizing. And this is a general trend which I feel we are already there, right? So by 2020, teleoperation, telepresence, ability to monitor and control and physical web world is already there. So somebody who predicted this in 2000 probably predicted right. So the ultimate goal of IoT is to automate human life but not control. Today, I don't know if we are getting into a stage of too many dependencies on automation and too many dependency on gadgets, which time will tell us, right? Few applications. Okay, few applications: home automation, manufacturing, medical healthcare, environment, infrastructure management, energy, transportation, right? So today we'll touch upon this environmental or agriculture kind of together. Okay. But I kind of work here, energy management and building and home automation. So this is where I work at Enlighted. So real-time applications. Yeah. So remote sensing, robots, drones, smart irrigation systems, supply chain, soil sensors, livestock monitoring, crop monitoring, smart irrigation, behavior monitoring, environmental monitoring, agricultural vehicles, and intelligence robots for fresh food or veg harvesting. Yeah, bear with me, I'm not able to skip that to the link. Okay, now while the ad comes up, all of these applications, are they built on the field or are they built in the lab? All these applications, are they built on the field, on the agricultural field, or are they built on the lab, inside the lab?
Built on the lab, used on the field.
Used on the field. So when you build it on the lab, you obviously have to depend on simulations, right? So we'll touch upon what is those simulations, how you can simulate those signals, and how you can scale it, right? So please remember all of this. I'm going to connect all of this in the later slides. All these are not CGIs. These are real devices that are there in some place or other. Gone. The grapes are gone. Blueberries are gone. Okay. So, IoT embedded system simulation strategies. So what is simulation? Simulation is the process of creating a virtual model to test and verify software with or without hardware. Sometimes with hardware, sometimes without hardware. Without the actual hardware of the system, without the actual field of application. So that is how simulation is defined, right? Now, what are the advantages? We can identify and fix issues early. It is flexible, decoupled software that is not hardware dependent, and the ability to get a working model in front of the customer early for feedback. So, assume building a cycle, which is very kind of easy, or assume building a UI screen. So, do we spend time in the iOS code or the Flutter code or the React.js code to get the customer feed, or do we do a paper napkin sketch and get the customer acceptance? This is how your screen will look. Are you okay with it? So what is the approach that we use? When the customer gives us a request, right? Even if that is too far, imagine building the house. Do we wait for the complete structure to come up and then look at the elevation? No. We do a paper napkin sketch, we do a civil planning and all of those, right? Now tie that with electronics. Tie that with mobile phone applications. So you kind of build the screen first in a PowerPoint or in a paintbrush or whatever tool that you want to use, and you get those acceptance. So these kind of simulations help you get there. Because if you depend on the code, you will spend at least 6 months to 1 year for you to come up with a proof of concept, right? So types of simulation: virtual hardware, functional simulation, hardware in the loop, system level, and behavioral simulation. So virtual hardware, often called as instruction set emulation, simulates the microcontroller or the processor at the instruction level. Let's say you take a STM32 microcontroller or any processor. There is a set of instructions that gets executed, right? So all of this will be simulated here. So it compiles the code, it launches the debug session and runs a virtual STM32. If you want to have an 8051 based processor and then control it, you need to really have a processor and then a keyboard attached to it. You program it into the memory and then you hit the run button and then it happens. With this emulation, what happens is, it already has that in a software code. And then using that, you start controlling the peripherals. Since virtual hardware simulates the CPU, verifying software will ultimately work together on the target can be a powerful technique. There are timers. There are timers involved with microcontroller development, right? So if you want to switch, you want to write a logic for timer and then test it. If these emulators are present, it will give you the timer output, timer count and everything. All that you do is verify the timer count and then do a if else and then control the algorithm. If it is not there, you have to physically configure the TCON register, scalers, pre-scaling, all of those, and then you have to verify if it is a ramp up counter or a ramp down counter, and then put the probe in it and then check for the pulses, measure all of those, and only then this timer initialization and configuration will take minimum 2 weeks to 3 weeks. With these emulations, you assume that it is already there. It can optimize the software. How this approach often has changed several challenges. First, open source evaluation, and some part is not supported, but we can skip the open source and go to the production. Predominantly, this emulation stage is no longer used because the processor itself today gives you a GUI based configuration. Previously, you have to look at the data sheet and get into the register and configure it yourself. Now the processors have evolved. The moment you get a processor, they always come with a UI where you can select the timer, how many timers, what is the scaling, and what is the count. All of this you select and click the button, it generates the hardware abstraction layer code, which came after 2012. Until 2012, 2011, it was manual configuration. You have to look at the register, you have to look at the prescalers, and which crystal to kind of get it started and all of those. Functional simulation. So customers are paying for features that they will use, not for the low-level firmware. The beauty of engineers is, the moment they see a problem, they'll start diving into it to fix it. It takes that maturity to step out of the problem and to see and analyze, right? And the moment we hear a requirement, we dive into it, starting to implement it. Now with these functional simulations, what happens is, you kind of assume that the function will work and you simulate the output to get a customer concurrence. So your lead time or the time for failure or the occurrence of failure is kind of preponed. You implement the software for 3 months and then the customer says this is not the way I expected. But instead you functionally simulate it and then you show it to the customer, this is how it will come. So that is where this functional simulation is helpful. Right? And this technique helps embedded to be flexible, scalable and hardware independent architecture. From day one, we can focus on customers' features, allowing them to be in front of it. They spend really 6 months to 12 months if it is a smaller application. If it is a wind energy application, the embedded systems team starts 5 years in advance. If it is a off-road vehicle, the embedded system hardware abstraction layer team starts 3 years in advance. If it is a IOT automotive application, they start, depending on the complexity, they start 3 to 5 years in advance. You would have recently heard all the Mahindra stories. They start 5 years, 7 years in advance. So all of these will help you kind of get your simulation up and running. And sometimes what happens is, why we are calling this hardware agnostic. You will start building your application based on some processor. By the time you come into production, that processor would have gone or the processor company would have gone. Right? That is one part of it. Other part, the processor could be stable. You will be visualizing a particular company sensor. There is no guarantee that the company will be alive for 5 years until you get to production. So what you write here is a scalable code, a configurable code, that the moment, if at all there is a change in the company, in the sensor and all of those, you kind of change this here. So predominantly now companies are looking at hardware agnostic, protocol agnostic and all of those, right? So functional simulation lets you focus on hardware agnostic manner, which helps save money, time, by not having to rework the system either because of customer or because of any other external constraints as well. It is very cheap to make those changes early in the cycle because your system is not fully developed. IoT cluster and app development. When we say cluster, imagine a vehicle infotainment system. That is predominantly called as a cluster and an infotainment system together now. And then your app development, this will kind of help you come into terms. Hardware in the loop simulation. Some companies also call hardware in loop simulation without the word "in." So this is HIL. Now, let's say there is a temperature sensor or a motion sensor. Now, the motion sensor typically gives you some kind of a digital output or an analog output. Same with the temperature sensor. When we start building the code, what happens is, whatever is the output that is given by the temperature sensor, you simulate it either through your function generators or your multimeter or your power supplies, and then provide it to your processor. You write the logic handling those, reading those and acting on those. Once your embedded algorithm gets stable, then you put in the real hardware. Until then, you don't put in the real hardware. Now, this will probably sound simple because we are talking only about one temperature sensor. Now, all the cars today have multiple temperature sensors and multiple speed sensors. So, when we take this to scale, simulating all of those hardware signals in one particular system in a controllable way is called hardware-in-loop simulation. So hardware-in-loop is designed to help you test the software with real hardware interfaces, but not the hardware in itself. Any doubts, questions, clarifications? Okay, so allows to, let's say we take a flight computer system, or today the car's computer is as equivalent to a flight computer in progress. Right? So it is all tested, simulated, and then taken to the field for validation. Allows the test interaction with virtualized sensors and actuators, bridging pure software simulation with full system, often used for simulation to vehicle validate diagnostic routine. So when a failure happens, what happens? If the system functions fine, the sensor is always giving you that input fine. When the failure happens, what happens? The sensor output. It goes crazy. Either it malfunctions or the data is malicious. Right? So that is one. And there are always sensors typically only to identify the failures also. Sometimes creating this failure is costly and time consuming. So what we do is, if it is a failure detection sensor, we know what is the output of that sensor. That output, we configure it in this hardware loop, and then we test it.
Sound.